All right, we're going to get started with today's class. Before I forget to mention it, the stuff that we cover today will not be on the next exams. This is all still exam 3 material starting towards the beginning of chapter 7. And then a couple reminders before we start. Tomorrow we have an exam review. So that's going to be Friday, March 25th. And the full schedule is posted on Blackboard for all the exam reviews if you want to plan ahead. So there's an exam review folder that has the schedule and also the documents that come out that are related to it. So that's going to be tomorrow, 2 p.m. in SEC 102. So they will all be that time and place on Friday before the exams. And it will be recorded, placed on YouTube, all that. And then also as a reminder, I sent an email about this, but in case you blow off my emails, office hours today will start not right after class, but not until 12:15 p.m. But then I should be available pretty much all the way until 3 if you want to come anytime during that period. So it'll be flexible after that, just a little bit later start than normal. Okay, so today we're going to, as I said, move on with some Chapter 7 material. And what we ended with last time was a definition of internal energy, and how really what we mostly are concerning ourselves with is the change in internal energy. So related to that, I want to introduce a concept of what a state function is and what it means to be path independent. This is not something that's going to come up all the time or be very important most of the time, but it is helpful to sort of understand how these types of parameters work. So what we mean by a state function, the simplest definition for us and how we can recognize it is a state function is anything with delta in front of it. So if it's, we talked about delta E last time, we're talking about it a little bit more today. We're going to talk about other state functions today, and they start with delta, meaning change in. So anything with delta in front of it can be classified as a state function. And remember that what it means is when you see delta, that means final minus initial. It's whatever the value is in the final state minus whatever the initial value is, and that gives you the change or delta. So we're going to talk again starting today with delta E. And so delta E is a state function, and what it means to be a state function and what it means to be path independent, those two things go together, is that delta E or any state function depends only on the final and initial states. It doesn't matter how we got there. All right, and so the concept of path independence means that if you know what the initial and final states are, that's going to define your state function, your delta E in this case, if we're talking in that context, and it's independent of path. It doesn't matter how we got from the initial state to the final state, the delta E will always be the same. So let's put some numbers on this to hopefully make it a little more clear. So let's say we have the initial and final states shown here on this slide. So the initial state has an energy of 10 joules, and the final state has an energy of 20 joules. Now, as we said last time, we don't typically measure absolute values of internal energy. We mostly concern ourselves with changes in energy or differences between them. But let's assume that's where we are in this case and that we know that. So then our delta E will just be the final minus initial. So the final state is 20 joules. The initial state has an energy of 10 joules, and delta E will just be plus 10 joules. All right, and when we say that delta E is a state function and its value is path independent, that means we can get a delta E of 10 joules no matter how we transform from our initial state to our final state. So there's an infinite number of possibilities that can get us there. I'm just going to show 2 of them here to kind of illustrate how there's different paths that can get us from the initial to final state, but they both would have the same delta E. So as we talked about last time, delta E is also equal to Q plus W. So when you're transferring energy between the system and the surrounding, it's always going to be in the form of heat or work or some combination of the two. So let's say we do this path here. Let's say we initially do 30 joules of work, which means work is done on the system. So when work is done on the system, the energy would raise by 30 joules, and we would get to this intermediate state that has 40 joule energy. But then let's say in the same process, the system releases 20 joules of heat to the surroundings. And so in this case, our delta E is Q plus W, which is 30 joules, minus 20 joules, which is plus 10 joules. So again, we got from the initial state to the final state in this way, but all that matters for determining delta E is what the initial and final state are. How we got there doesn't matter for the delta E value. Because we could also go many other paths to get to the same initial and final state. So let's say we did initially let's say we initially release 20 joules of heat. We do it in the opposite order. If we release 20 joules of heat first, that gets us down here to a state that would have an internal energy of minus 10 joules. And then let's say from there, we do 30 joules of work on the system. Delta E is Q plus W, and it's still going to be plus 10 joules. So no matter how we get from the initial to the final state, our delta E is always the same. So heat and work, Q and W themselves are not state functions. Their value depends on the path we take, but if we add them together and determine delta E, the overall delta E value is just determined by the initial and final states. So that's what it means to be a state function. Like I said, that concept's not going to come up a lot, but we are going to talk about a few different state functions, at least one other one in particular today. So it's helpful to know what it means when you see delta in front of something, and a little bit about path independence is sometimes helpful to think about as well. So before we move on to the next state function, we're going to talk just a little bit about work. So we have these two terms that determine delta E, Q and W. We're going to talk about heat, Q, a lot today and a lot throughout this chapter, and then we're just going to talk a little bit about work right now. So it's basically just one slide or in an example problem. So the only type of work we're going to talk about is called expansion work. Now this concept will make more sense after we've covered chapter 8, which is on gases, because it involves gases. So chapter 7 and 8 will be tested together, so if this doesn't make perfect sense now, it should make better sense after chapter 8, and you'll be good before the next exam. But expansion work is when a gas expands against an external pressure, and we're going to talk about only one specific case of that. So first we have to define a few things that we'll come back to in chapter 8, as I said. So pressure is force divided by area. So every gas exerts a pressure, which is, again, is the force that it exerts divided by the area that is pushing against. And there's a lot of different units for pressure, and we'll cover more of them in chapter 8, but the one that we'll use in this chapter is going to be atmospheres, ATM, which is essentially the pressure of gas at, or the pressure of the air at sea level, is how that atmosphere is defined. So 1 atmosphere is the sea level air pressure on average. Now, when we talk about expansion work, we're talking about a gas expanding against a constant external pressure. And so there's one simple equation that will tell us what that work is. It's going to be equal to negative of that external pressure times the change in volume, delta V, as the gas expands or contracts. So again, when a gas expands or contracts, its volume is changing. It's getting bigger if it's expanding or getting smaller if it's contracting. And the work that's associated with that process is equal to this if the external pressure is constant. So this PEXT is our constant external pressure in this situation. If the external pressure is not constant, then we have to calculate work differently, but we're not going to talk about that in this course. That's a bit more advanced of a topic. So we're just going to talk about this one situation where external constant pressure and delta V, again, delta meaning final minus initial, as it always does, is our change in volume, final volume minus initial volume of the gas. And there's going to be a conversion that you're going to have to do from time to time in these problems, because usually we report work or heat or delta E or whatever combination of those we're talking about is going to be in units of joules. That's the standard unit for energy or anything related to that. But in this equation here, our external pressure is usually going to be in atmospheres, and our volume is going to be in liters most often. So that means the product of these two is going to be a weird unit that's going to be atmospheres times liters, a compound unit. If we want to get that into joules, that's going to be 101.3 joules. So we kind of have to remember that conversion, or at least we'll make sure you know how to use it when the time comes, because our initial answer, when we just multiply external pressure times delta V, is going to be in a weird unit, atmosphere liters. We have to convert to joules in that way. So that's another thing that's a little bit important to know for this. Now, if we think about the signs for this process, so again, work can be positive or negative. We said last time that positive work means the system is doing work. Positive work means the surroundings is doing work on the system. Negative means that the work is being done by the system. So you have to keep that straight, which I just did not do there. But at any rate, the equation sort of tells us that directly. So if our final volume is larger than our initial volume, which means the gas expands, that means our delta V has to be positive. Whenever the volume is getting bigger, delta V is positive. And from the equation, which has a minus sign out in front, that means our work is going to be negative. So when the gas is expanding against the constant pressure, that means the gas, which is our system, is doing work against the surroundings, and that's why the work term comes out to negative. And again, this all comes out in the equation, so you don't necessarily have to remember this, but having some sort of internal concept of the different signs that are possible is helpful for this whole chapter. And so when the system is doing work, the work term is going to be negative, and that means we're expanding the volume. And then the opposite is also possible. So if our final volume is smaller than the initial volume, that means the gas is being compressed. That means our delta V is going to be less than 0. It's going to be a negative change in volume. And from the equation, which has a minus sign out front, that would make work positive, greater than 0. So when the gas is compressing, when it's being compressed by the external pressure, that means the surroundings, the external pressure, is doing work on the gas, and that gives you the positive W, positive work term. What's that? W stands for work, right? W stands for work, yes. So work is done on the system when the gas is compressed, and that's going to be positive. And again, we're only dealing with this one specific type of expansion work, or compression work as it's sometimes called, and these are the two possibilities that you'll have. Now, the other thing to keep in mind is if you have 0 external pressure, which would be when you have a vacuum outside of your gas, then if this is 0, the work is also 0. So it can expand freely if there's no constant external pressure, in which case there'd be no work done. But if there's a non-zero external pressure is always going to be either 0 or a positive number, then there will be a non-zero work term associated with that. So let's just do one example problem of this. So here we have, let's say we do a reaction at constant temperature and it produces a gas, and we say that the volume expands from 1 liter to 10 liters against a pressure of 0.978 atmospheres. Calculate the work done. So again, it's this picture here. We're starting with a gas that has a volume of 1 liter, and there's a movable piston or a movable sort of lid that can expand or contract as the gas allows, and then after the chemical reaction, the volume has expanded to 10 liters. The external pressure is constant at 0.978 atmospheres. So in these types of problems, all you really need to do is just multiply the numbers that you're given. So using that simple formula, negative of the external pressure times delta V, our external pressure is 0.978 atmospheres, so that goes out front. Then we have to multiply by delta V. Remember, delta V, anything with delta is just going to be final minus initial. So our final volume is 10 liters. Our initial volume is 1 liter. So that means our delta V is going to be 9 liters. I guess we have a little bit of a... Oh, I guess I gave you more significant figures than that in the problem. Let me fix that. So the diagram doesn't have 2 decimals, but the numbers in the problem do, so let's use that correctly. All right, but anyway, it's still the same number, but just one more digit. 9.00 liters is our delta V. So we just multiply that, and we get minus 8.80, and then again, compound unit, atmospheres times liters. So that's a weird energy unit. It's not wrong to report the number this way, but at the same time, we don't normally do that. And I didn't specify units in this problem, but I should have. We're going to usually calculate the work done in joules. Not always, but that's the most common way we'll do it. So then we just have to do one conversion to get that into the right unit. So the work in joules is going to be that initial value we got in atmosphere liters, or liter atmospheres as is more commonly written sometimes. And we're just going to use the conversion that I introduced last time, 101.3 joules per liter atmosphere. And that comes out to minus 891 joules, which that would be the unit that is most common to report work or energy or heat in terms of. Okay, so that's how we do that. So again, this is really the only type of work you're going to deal with. Pretty simple equation, and that's all there is to it. So any questions on that? All right, so the next thing we're going to go into is another state function called enthalpy. Which is probably a word you've heard before if you've taken chemistry in the past, but we're going to define it here and then talk about how we sort of different ways that we can measure enthalpy in a reaction, or we can, sometimes calculate it in different ways. So we'll talk about both of those. So the reality is that in chemistry, we're mostly studying chemical reactions. That's what I said is going to be the context that is most important for studying heat and work and energy and all that stuff. And when you do a chemical reaction in a lab, they're usually, but not always, but usually done at constant pressure. So when you do a reaction at constant pressure and you want to measure the change in internal energy, delta E, remember that's going to be a function of Q and W. And as we just talked about with expansion work, if you're doing a reaction at constant pressure, you're going to have a work term that's defined as the negative external pressure times delta V, or more simply as just minus P delta V. If it is constant pressure, you can just write it as just P. But nonetheless, what this means is that if you want to measure delta E for a reaction, you have to measure the heat and the work. So you have to consider what the heat is for that reaction, which is going to be a function of the change in temperature. We'll get into how to calculate that a little bit later today, but then you also have to calculate work. So to get delta E, you have to really measure two things. So it's not the most convenient state function to use when studying chemical reactions, because it requires essentially two numbers that you have to input to be able to get delta E, one value. And so what we're going to do here is we're going to define a new state function. So let's say that we're doing this at constant pressure. The heat that we measure, we're going to call Q sub P. And so then what we can do is we can rewrite delta E as at constant pressure, the heat is QP, just signifying that it's measured at constant pressure. And then we're going to replace work with minus P delta V. So if we're doing a reaction at constant pressure, this is a way that we can rewrite our delta E. And then what we're going to do is we're going to solve for QP. So it's relatively straightforward to measure the heat for a reaction, Q. We're going to talk about how to do that today. So we can measure QP very easily, much more easily than we can measure P delta V. And so if we solve for QP, we get delta E plus P delta V. So this Q sub P, this heat that we measure at constant pressure, it's a sum of two state functions, delta E and P delta V. If it's a sum of two state functions, it itself must also be a state function. And so we rewrite this and label it as delta H, where H is going to be enthalpy now. So we've defined a new state function, enthalpy, delta H, which is just going to be simply measured as the heat at constant pressure. So if we do a reaction at constant pressure, which is the most common way to do reactions in a lab, then we just have to measure the heat term, and that directly gives us this new state function delta H, which is enthalpy. All right. So H stands for enthalpy. I don't know why it has the label H, but it does. And it's going to be equal to energy plus PV. So if delta H is delta E plus P delta V, H itself is going to be E plus PV. Again, just like most state functions, we don't consider absolute values of H. We mostly consider changes in enthalpy, especially when we're studying it in the context of chemistry and chemical reactions. But this would be how H is defined. And so what the significance of this is that delta H is a new state function that we've now introduced. And it's much easier to measure because it's just determined by the heat at constant pressure. Now this topic of enthalpy, this is one of those many topics we have that's going to be covered at the surface in this class, and then you're going to come back to it in much more depth in Chem 2. So if you take the second semester of this, you'll see enthalpy again in a different light, in a more detailed treatment of that and its significance. So in this class, we're not going to really get into too much detail about the real significance of delta H and why it's important in chemistry as much as you will in Chem 2, but we're going to talk about, again, what it is, how to define it, which we did here, and especially then how to measure it in an experimental setting or by calculating it in different ways from sort of first principles, or at least from empirical tabulated values. So we're going to talk about how to calculate delta H a lot, but we're not going to know too much about its significance. But what it refers to, again, is the heat of a reaction, the heat as the reaction progresses when the reaction is carried out at a constant pressure. Now you might think that, well, delta H is, does it have the same meaning as delta E? Not exactly, as we said, but is it sort of related? And again, it is related by this equation that we gave. It's delta E plus P delta V. So you might be wondering, well, how do these two values compare to each other? Because delta E is the change in internal energy. That's a pretty, significant quantity for any system that you're studying. So how does delta H compare, and what does it really tell us? Now, the reality, the long story short, is that in almost every situation when we're dealing with sort of regular chemical reactions that we would study, delta H and delta E are actually very similar to each other in terms of their value and in terms of how they can then be interpreted. So let's talk about a few different situations and how delta H and delta E would compare to each other. So if we do a reaction that does not involve a gas, so reactions involving solids or liquids or aqueous solutions like we talked about in the last chapter, in those cases you typically would have very small volume changes during the reaction. Because those condensed phases, again, something we'll get to in more detail in chapter 9, but when you have condensed phases, liquids, gases, solutions, their volume does not doesn't change a lot, even if you change the identity of the substance or even if you change the temperature of the reaction as it goes along. The volume is pretty insensitive in those cases when you're not dealing with gases. So because of the volume change is very small, in most cases negligible, this P delta V term would be approximately 0. Because if your delta V is 0, then the product of P delta V equals 0. So if this P delta V term is 0 or close to 0, then delta H and delta E are basically the same. So for reactions that don't involve gases, those two terms are basically the same. Not exactly the same, rigorously speaking, but to the precision that you can typically measure it or typically care about it, those two values are the same. Now, there are going to be situations where the reactions involve gases, either on both sides of the arrow or on one side of the arrow. And in that case, then there could be some significant differences between delta H and delta V. So one example, though, is if we have a reaction where the moles of gas do not change. So that means we have the same number of moles of gas on the reactant side and the product side. So let's talk about this one here. Hydrogen gas plus chlorine gas reacting to form HCl as a gas. So all in the gas phase, no liquids, no solvents around. But in this case, what we'll notice is that we have 2 moles of gas on the left side of the arrow, on the reactant side, 1 mole of hydrogen, 1 mole of chlorine. And we also have 2 moles of gas on the product side, just 2 moles of the product HCl. So we have 2 moles of gas on each side of the arrow. So if the moles of gas is not changing, again, something that will be more obvious once we study Chapter 8 material, but if you're not changing the number of moles of gas, you're also not going to change the volume of the gas that's present during the reaction. So in this reaction here, where we're keeping the same number of moles of gas, P delta V is exactly equal to 0 when you don't change the moles of gas, and that means delta H is exactly equal to delta E in an ideal sense. This involves the assumption that these are ideal gases, which we'll define more in Chapter 8, but in that ideal case, P delta V is 0, delta H equals delta E. Now, there are going to be some reactions where the moles of gas does change. So if we have carbon monoxide and we react it with oxygen gas, that can form CO2, carbon dioxide. And what we'll notice here is that we have 3 moles of gas on the reactant side, 2 CO plus 1 O2 is a total of 3. On the product side, we only have 2 moles of gas, so we're going from 3 moles of gas on the reactant side to 2 moles on the product. The number of moles of gas is getting smaller. That would mean that the volume will also get smaller if the reaction is done at a constant temperature. So again, that'll be more obvious in Chapter 8, but what this means is that if the moles of gas is changing between reactants and products, whether it's getting bigger or smaller, this P delta V term is not going to be equal to 0. It's going to be a non-zero value, and that means our delta E and our delta H will not be equal to each other either. But that said, for the typical pressures and volumes that we're working with in a real setting, it's still going to be true that P delta V is a lot smaller than the heat that resolves from the reaction. So again, it's the delta H is determined by a sum of 2 factors here, but this P delta V term is actually a pretty small component of that. So it's still going to be true that even in these situations, delta H and delta E are not too different from each other. It might differ by a few percentage points, you know, in terms of the absolute value, but it's not going to be a huge difference in most cases, but they're not going to be exactly the same.
What is like the 2-hour sample, like, why just like V delta V? What is that simple sample, the one between V delta V and?
That means not equal, so it's an equal sign with a cross through it telling you.
I'm not talking about like the one, but like.
So that's much less than. So in P delta V is usually much smaller than the heat that you measure. So the heat is the measure of delta H, but the contribution of P delta V to that is pretty small in most cases. And so that means that in general, again, delta H and delta E are not too different from each other. A little bit different in this situation where the moles of gas is changing. So I don't think we're going to talk too much about the quantitative aspects of this. There is an equation that relates delta H and delta V, or sorry, delta H and delta E, that's in terms of how many moles of gas you have on each side of the reaction, but we're not going to cover that in this course. Maybe it'll be in Chem 2. So there is sort of ways to calculate the differences between delta H and delta E quantitatively for a specific reaction. But just for now, just take my word for it that those differences are typically pretty small on the magnitude of the delta H that you're measuring. All right, so that's, you know, even though delta H is different than delta E in terms of its definition, the value that you get for it in most cases is pretty similar, and it can be interpreted still as sort of a change in energy or a heat in the case of a chemical reaction. So with delta H introduced, we now have a couple of new terminologies to introduce as well that are related to it. So we have exothermic and endothermic. So exothermic is a situation where the heat or at constant pressure, which is equal to delta H, is less than 0. So whenever heat is less than 0, that means is heat is released to the surroundings, and what you can almost think about it as is that heat is released as a product of the reaction. Now, heat, as we know, is not a substance, so you wouldn't technically write it on the product side, but you can think of it in an exothermic reaction as heat is being given off by the reaction. And so that means that heat is released, delta H is going to be negative. So the classic example of exothermic reactions are anytime you burn something. So there are general chemistry professors that are brave enough to do this demonstration in class. I'm not one of them. So if you take hydrogen and, you know, mix it with oxygen and give it a little spark, it will, you know, ignite and burn pretty rapidly and pretty spectacularly. I definitely don't want to do that in a carpeted education building classroom. That would be a risk not worth taking. But nonetheless, if you burn anything, including hydrogen, we know that those are releasing a lot of heat to the surroundings, right? Because anytime you burn something, that's what the flame is. It's the heat that's being produced by that chemical reaction, that combustion reaction. And so you can, again, think of heat as being a product of the reaction if you want to think about it that way. So that's what an exothermic reaction refers to. And so when you do an exothermic reaction, it's giving off heat to the surroundings, and that means the temperature of the surroundings increases during an exothermic reaction. And I know we don't use these very much in the Houston area, but if you've ever seen these hand warming packets, if you ever travel to go skiing, or I used to use them when I worked at a symphony hall in Cleveland where I had to stand in the freezing cold garage for 3 hours helping people get into the building. And so I would hold these in my pocket to keep my hands warm. And so basically these are little packets that have little pieces of iron inside of them, and then like some sort of other substance that helps catalyze the reaction, make it go faster. When you open them up to air, the iron starts rusting really fast inside and it generates some heat that warms up the heat pack. So that would be another example of an exothermic reaction. Anything where the surroundings get warmer is an exothermic reaction happening. And then the opposite is called endothermic. So basically everything I said above, just make it the opposite, and you'll find out what endothermic means. That means that the delta H is positive, which means that heat is absorbed during the reaction. And it can be shown as a reactant. Again, not technically correct to do that, but it's helpful for thinking about it. So endothermic reactions are not as common, I would say, and not as many that you would know of in your everyday life. But if you have a cold pack like this, so if one of these instant cold packs where it's, you know, initially it's room temperature, and then you just crack a little thing on the inside and all of a sudden it gets cold. So what that's doing is it's allowing a salt to dissolve in water. Well, there's a few different ways that these ones work, but one possible endothermic reaction is if you take solid ammonium nitrate, it absorbs heat from the surroundings as it dissolves in water and makes the aqueous ammonium nitrate solution. All right, so this is an example of an endothermic reaction, but whenever the reaction is endothermic, you can think of heat as being a reactant. That means the reaction is absorbing heat from the surroundings, and as a result, the temperature of the surroundings decrease, so they'll feel colder as that reaction happens. All right, so that's some concepts about endothermic versus exothermic reactions. What does T stand for? Yeah. Temperature. Yeah, capital T is pretty much always going to be temperature in this course. All right, so that's going to be the difference between exothermic and endothermic, and what we're going to be mostly talking about again is how to calculate them as we get through this. So with that in mind, we can draw some enthalpy diagrams for chemical reactions just to, again, further drive home the point of how this works. So as I said, we don't normally measure absolute enthalpy values for chemical substances, but if we were to think about them in that way, when you have an exothermic reaction, delta H being less than 0, that means, remember, delta H means final minus initial. In a chemical reaction, the final state is the products, the initial state is the reactants. And so when you have an exothermic reaction, that means your reactants have higher enthalpy than the product. The enthalpy is decreasing during the reaction. So on an absolute enthalpy scale, the reactants would be higher than the products. And so you have a negative delta H as you go from reactants to products. The enthalpy decreases, and that means heat goes out of the reaction. All right, so that difference in enthalpy, that you're losing enthalpy during the reaction, and that enthalpy is being released now to the surroundings, and that's what warms the surroundings. And then for an endothermic reaction where you have positive delta H, final minus initial is positive. That means the final state, which is your products, has a higher enthalpy than the initial state, the reactants. So as the reaction progresses, the enthalpy is increasing, meaning your delta H is positive. In order for that to happen, you have to have heat going into the reaction, which is why the temperature of the surroundings would get lower as that occurs. Heat is going into the reaction. So that's just another way of thinking about exothermic versus endothermic. Again, in a chemical reaction, the initial state is reactants, final state is products, and the relative enthalpy of those two states is going to determine what the sign of delta H is, whether it's exothermic or endothermic. But the most important thing we need to do in this course, in this part of the course, is learning how to calculate heat and calculate enthalpy and relate the two to each other. So now we're going to talk about sort of the more quantitative side of things of how do we calculate. We talked about work a little bit earlier today. Now we're going to talk about heat. How do we calculate Q? And then, of course, how do we relate that to an enthalpy change for a chemical reaction? So let's think about this conceptually first to build up this relatively common and relatively simple equation we're going to use for heat. So we have to think about what things is heat proportional to. All right, so let's say we have some boiling water, and you spill one drop of that on your hand. It's going to sting, but it's not going to do too much damage. But then let's say you spill a whole pot of water on your hand, then you're going to be in serious trouble, right? So which one do you think gives off more heat as it contacts your hand? The drop of water or the whole pan of water? I heard some mumbling. I'll assume you said the right thing. So if you have more mass, you have more heat, right? If you have more water, more hot boiling water, that's going to give more heat to the surroundings as it comes in contact. And so heat is proportional to the mass that you have. The more substance you have, the more heat that's going to be involved in that. So heat is proportional. That's what that little alpha type character means. Proportional to mass. And then another one that's going to relate to is the temperature. So remember that we talked about heat is a form of energy transfer that involves a temperature difference between the system and the surroundings. So if you want to take, let's say you have a pot of water on the stove and you want to heat it up to a warm temperature like 40 degrees Celsius versus you want to heat it up to boiling. Which of those do you think requires more heat? Heating it up to 40 degrees Celsius or heating it up to 100 degrees where it boils? Right, heating it to boiling is going to require more heat going into the water. So heat is also going to be proportional to the change in temperature. The bigger the temperature change, the larger the magnitude of the heat term that's going to be involved. So it's proportional to two things. It's proportional to how much substance you have that's undergoing that transfer of heat, and it's also proportional to how big the temperature change is. So in chemistry, we may have used this trick before, and we're going to use it a lot in the next chapter as well. If Q is proportional to two things separately, it's also going to be proportional to the product of those two things. So heat is going to be proportional to the product of the mass of the substance and its change in temperature, delta T. And then another trick we've talked about is that if you want to change something from a proportionality sign into an equal sign, you just need to add a constant to one side of that equation. So the way we write it as an equality is that Q is going to be equal to mass times a constant C times delta T. So we'll define here what the heat capacity is, C. So specific heat capacity is abbreviated as lowercase c. And what this is going to refer to is the amount of heat needed to raise the temperature of 1 gram of substance by 1 degree Celsius. So this is going to be what our proportionality constant is. It's called the specific heat capacity. And it's going to be different for every substance. So specific heat capacity is unique for every substance that we have. But when you're calculating heat involved in that, in changing the temperature of that substance, you have to put that in to account for that. And it's the amount of heat necessary to raise the temperature of 1 gram of substance by 1 degree Celsius. So the most common one and the only heat capacity, specific heat capacity that you'll need to remember, because it's going to come up all the time, is water, which has a specific heat capacity of 4.184 joules per gram degree Celsius. All right, so that means it takes 4.184 joules of heat to raise the temperature of 1 gram of water by 1 degree Celsius. And so that's the sort of constant you would put into this equation along with the mass of the substance and its actual change in temperature to calculate the actual value of Q that's involved in whatever process you're studying. Now I want to bring up a little bit of a important point here that often is a source of confusion for students in this part of the course and a little bit also in the next part as well, which is what are the units for delta T here? So I'm showing you here as 1 degree Celsius. But in terms of delta T, you can also do it in Kelvin. So when you're reporting a delta T, a change in temperature, you can use temperatures in Celsius or Kelvin. Now you might be wondering, like, well, why is that the case? Why can we use either one? Doesn't the units matter? Well, that's because it's a difference in temperatures, and the size of 1 degree in Celsius and Kelvin is the same. So as an example, let's say we have the initial temperature is 20 degrees Celsius, which is equal to 293 K. So we do need to, not so much in this chapter, but in the next chapter, we need to learn how to convert Celsius to Kelvin. You just add 273 to get from Celsius to Kelvin. And let's say our final temperature is equal to, let's do an easy one, 25 degrees Celsius, which is 298 K. So delta T, which is going to be final minus initial, if we do it in Celsius, it's going to be 25 Celsius minus 20 Celsius, which is plus 5 degrees Celsius for delta T. Or if we do it in Kelvin, 298 Kelvin is our final temperature. Our initial temperature in Kelvin is 293 Kelvin. That's going to be plus 5 Kelvin. So for a change in temperature between two different temperatures, whether you input those initial temperature and final temperature as Celsius or Kelvin, doesn't matter, just keep it consistent, and you'll get the same delta T in either unit because the size of 1 degree is the same in those, they're just shifted in terms of their absolute scale. All right, so don't let that be a source of confusion, but whichever temperature unit you're more comfortable with, you can certainly use, but in problems like this where delta T is important, you don't need to worry about temperature conversions. Just use whatever units you're given. Make sure you subtract the two if you're trying to get a delta T where you have two given initial and final temperatures, and then you can just, again, keep it in Celsius or Kelvin and it'll work. So you can also write this as 4.184 joules per gram Kelvin, because if the delta T is in Kelvin, you can still put it into the same equation without having to change your heat capacity, because again, this is per delta T, per a change in temperature. All right, so hopefully that's clear, and as we see it more, we'll point it out. But any questions so far on the concept of calculating heat? All right, so what we're going to proceed to now is one other related heat capacity, which is called molar heat capacity. This one is not nearly as common, and you're not going to have to, I don't want you to worry about memorizing the values, but molar heat capacity is the amount of heat needed to raise 1 mole of substance by 1 degree Celsius. To raise the temperature of 1 mole of substance by 1 degree Celsius. It's not as common, but again, the heat equation that we just covered can be also written in terms of moles as well. So this is an alternative form of that. So 1 degree Celsius or 1 Kelvin. And the abbreviation is annoying, unfortunately. It's often abbreviated as capital C instead of lowercase c. Why the powers that be did that is beyond me. Or sometimes you'll see it as C with a little m next to it to tell you that is a molar heat capacity. Again, don't worry too much about the abbreviations. In context, it will be obvious, and based on the units that you have, it will be obvious whether it's a molar or a specific heat capacity. Specific heat, as I said, is much more commonly used, but molar heat capacity, you can do it as well. So for water, if you want to calculate the molar heat capacity, we start with the specific heat capacity, which we'll have to know for water. And then to convert this into a molar heat capacity, we just need the grams in the denominator to convert into moles. And so how do we convert grams to moles? Well, we did that a million times in Chapter 5 and Chapter 6. We just used molar mass. So the molar mass of water is 18.02. So there's 18.02 grams per mole. That cancels out grams here and leaves us with moles in the denominator. And so numerically, that's going to come out to 75.40 joules per mole degree Celsius or mole Kelvin. All right, so that means it takes 75.40 joules to raise 1 mole of water by 1 degree Celsius. And so we could also use that as an alternative form of heat capacity to calculate heat in terms of moles of substance. But we're not going to probably see that a lot. I just want to make sure you're familiar with it because it may come up on some of the assignments. Okay, so those are the two ways of denoting heat capacity. Now let's just go through and talk about a bunch of examples then and how we use that equation, and then again bringing it back to enthalpy eventually as we go through. So let's say we do an aqueous chemical reaction in 50 milliliters of water. So when you do an aqueous chemical reaction, the water that's the solvent can be thought of as the surroundings for the reaction. It's what's the reactants and products are dissolved in that water, and so any heat that's generated during the reaction will be released into that water, which can be thought of as the surroundings. And let's say during this reaction the temperature raises from 22.31 degrees Celsius to 28.37 degrees Celsius. Determine the heat absorbed by the water. So anytime we ask you about heat and we want you to calculate it, you should immediately think of that equation, MC delta T. So in this case, we're determining the heat absorbed by the water. So we need the mass of the water. We need the heat capacity of water, because remember that heat capacity, specific heat capacity, or any heat capacity is substance dependent. So it's going to be for that specific substance, and we need the change in temperature. So to calculate Q, we need those three things. Now, none of them are directly given to us in this problem, but we can find them out pretty easily. So first, the mass of water. Something we're going to have to get used to now in this part of the course is we usually measure solvent volumes in milliliters or liters, but we need to put mass into these types of equations. But for water, it's exceptionally simple because the mass of water is just going to be the volume, and then we multiply by the density. Density of water is 1, so this is a trivial calculation that you don't even really have to do. So however many milliliters of water we have is the same as the number of grams of water we have, because the density of water is 1. All right, so if we have 50 milliliters of water in this reaction as the solvent, that's the same as having 50 grams of water. So that's going to be the mass that we put in here for this equation. And then the specific heat capacity for water, since we're in grams, we'll use that one. This value, I think we'll sometimes give it to you, sometimes not. I don't know why we're inconsistent like that. But nonetheless, you should know it because you're going to use it a million times. 4.184 for water is the specific heat capacity. So then we just need the delta T. So delta T is always going to be final temperature minus initial. Delta anything is final minus initial. And so for this process here, it's raising from 22.31 to 28.37. So final temperature is going to be 28.37. Initial temperature is 22.31. So delta T is going to be 6.06 degrees Celsius. And again, as we talked about, delta T is going to be the same whether you do this in Celsius or Kelvin. We were given temperatures in Celsius, so we can leave them as that, but that would be also a delta T of 6.06 Kelvin if we had converted both to Kelvin first. So either way, you'll get the same number. And then you'll put that up here into the equation for heat, MC delta T. So that gives 1268 joules. Sometimes, a lot of times we'll ask for heat in kilojoules, so you should know how to do that. You just divide by 1,000, which would be 1.27 kilojoules. I don't think I specified here the units, but for a number that big, you'd likely have it in kilojoules instead of joules, but both units are possible. So you just divide by 1,000 to go from joules to kilojoules. Okay, so that's how we use that equation. And just mostly just making sure you're using the right numbers, plugging them in, and multiplying them. It's not terribly difficult. So any questions so far? Yeah. It's not a parentheses, it's a degree Celsius. Sorry. All right, so that's the units, degrees Celsius. Yeah, so that's going to, you just subtract the two temperatures to get delta T. All right, now that's a pretty straightforward application because we were just using the equation, calculating Q, and there's really no additional effort needed. But a more common situation that you'll come across is using that equation to figure out something else about that. So not just calculating Q, but calculating one of the other terms. So let's say we have a 1 ounce gold coin with a specific heat capacity of 0.129 joules per gram Kelvin. So metals have very small heat capacities. That's a property of metals that we'll talk about in chapter 9. So it's much smaller than water, 0.129, and compared to 4.18 for water. But anyway, if we have a 1 ounce gold coin and it absorbs 721 joules of heat, how much does its temperature increase? So this is, same equation, same concept, just solving for something a little bit different here. So anytime you talk about heat, you should think about this equation. It's really the only equation for heat we're going to have, MC delta T. But what we're doing here is we're solving for delta T, how much the temperature increases. So we just rearrange this. It's going to be Q divided by MC. And so we just have to start putting the numbers in that we have. So the heat is 721 joules. Now we do have to be a little bit careful with units here because the heat capacity is given to us in 0.129. The most common units that we have are joules per gram, and then whatever temperature unit we have, Kelvin or Celsius. So heat has to be in joules, which it is. So you have to make sure you put the heat in the correct unit, which is joules. But our mass will always need to be in grams if we're using this standard form of the heat capacity. So this is a 1 ounce gold coin, so we need to convert it into grams. This is not a conversion factor you would have to know because it's not a very common or standard one. But I told you here that 1 ounce is 28.35 grams. So that's just 28.35 grams for mass. We have to make sure we put that in the correct units. So writing out units is still going to be important. I've emphasized it over and over again. So that's the mass we put in there, and then the heat capacity, we can leave it in that unit. 0.129. I wouldn't recommend trying to convert the units on the heat capacity. It's usually easier to convert units on the other given quantities instead of trying to convert your heat capacity. In principle, it works either way, but the heat capacity is a compound unit, joules per gram Kelvin, so sometimes getting the conversions right is a little bit more tricky. So what we get here is 197 Kelvin, so a pretty big temperature increase from this amount of heat. All right, so that's just a problem where we would calculate something else from that equation, but just using that as an unknown. All right, so that's how we use that equation a couple different ways. So the next related topic we're going to move into is going to be calorimetry. So this is sort of an experimental parallel to the heat equation we've been talking about. So how do we measure this experimentally and use that equation Q equals MC delta T in the experimental setup? Again, in the chemistry labs, I don't know for sure if you guys do a calorimetry experiment, because I don't know for sure of anything that goes on in there, unfortunately. And I've tried to find out, but they don't tell me. That's not true. I just don't ask. But if you, I should know because they are related. So there's probably a calorimetry experiment at some point in either Chem 1 or Chem 2. Usually you do it in like a coffee cup or a thermos, I think, if that sounds familiar. Maybe you haven't gotten there yet. But anyway, a calorimeter is a device used to measure heat. That's really what the simple definition is. So when we're doing experiments in a lab that involve measurements of heat, this is the device you would use. And they can be of varying complexity depending on the system you're studying and depending on how precise you need to be in your measurements. But it's a device for measuring heat, and the most important thing that it does is that it contains the surroundings. Because remember that what we said was, whenever you have heat transfer, you're transferring heat between the system and the surroundings, and technically speaking, the surroundings is the whole rest of the universe. And so if your heat is just dissipating into the whole, out into the world, like you're not going to be able to measure it very easily. So what a calorimeter does is it contains the surroundings. It insulates the whole rest of the world from the little, part that you're studying, and allows you to measure that transfer much more accurately, much more easily, because it contains those surroundings. Basically, it insulates the surroundings from the system. So usually a calorimeter is filled with water. So water is going to be the substance in the calorimeter that absorbs the heat, and then you would have varying levels of insulation that would keep that water that's in the calorimeter from transferring its heat out into the air and out into the surroundings. So it's insulated to make sure that all the heat that's transferred goes into the water and stays in the water for a long enough time at least to measure it. So that's really what a calorimeter is. So it have usually a thermometer to measure a change in temperature, water to absorb the heat, and insulating material on the outside to keep that heat from going off into the world. So there's a few different applications of calorimetry we're going to talk about. So one of them is going to be calculating the heat capacity of an unknown substance. In other cases, we're going to use a calorimeter to calculate delta H for a reaction, change in enthalpy. So there's kind of different ways that we use it, but the key step in all of these is going to be to calculate the heat that's absorbed or released by a calorimeter. So again, the calorimeter absorbs the heat from the system or gives heat to the system depending on the sign of Q that's involved. And so you have to be able to calculate that, and that's going to be where we use the MC delta T equation. So there's different situations that we're going to be dealing with those. So in the simplest case, we don't really tell you anything about the calorimeter except for how much water is in it. So in that case, we're assuming that all of the heat is absorbed by the water in the calorimeter, and Q is just going to be given by MC delta T. Mass of the water that's in the calorimeter, heat capacity of water, times delta T. Where again, the heat capacity for water is going to be that familiar 4.184 number. All right, so that's kind of the simplest situation where we're assuming that the water in the calorimeter absorbs all the heat and nothing else is really involved. Now that's an approximation. That's not going to be the most accurate way to do calorimetry, but for some systems that's certainly not bad, and that's probably the way you'll do it in the chemistry lab, at least at the outset. Now the other thing that sometimes happens in a calorimetry problem is that we only give you just the overall heat capacity of the calorimeter, which would include the water in it, which would include all the things that make up the calorimeter, the thermometer, the enclosure, the container, whatever, everything else. But we just give you a single value for heat capacity, which is not a specific heat capacity. It's not in terms of mass. It's just an overall heat capacity. So in that case, all you do to calculate heat is just take that heat capacity for the calorimeter, which I'll abbreviate as C sub cal, and multiply by delta T. And in this case, the heat capacity of the calorimeter is going to be given in units of usually joules per degree Celsius or joules per Kelvin. Where again, it's an overall heat capacity. The mass is sort of built into that. You don't have to use the mass separately because it's just the whole heat capacity for everything that's in the calorimeter all just kind of glommed together. So that's another sort of variation, which is fairly simple to deal with. You have to remember that in this case, there's no mass term because the heat capacity includes the entire calorimeter and all the water that's in it all together. Now the other situation, which is the more complicated one, but it's just a sort of a combination of these two, is We will tell you how much water is in the calorimeter that's absorbing some of the heat, and we will also tell you the heat capacity of the empty calorimeter, which you would then say is absorbing some of the other heat. So in that case, the heat is going to be a sum of those two. It's going to be the heat that's absorbed by the calorimeter itself, which is again given by its heat capacity times delta T, plus the heat that's absorbed by the water in the calorimeter. So this is sort of the most accurate way of doing it, because what you're doing here is you're measuring a heat capacity for everything else that's in the calorimeter, the surroundings, the thermometer, all that, and you're measuring how much water is in the calorimeter and accounting for its heat absorption explicitly as well. So that's the more complicated situation. So it's going to be one of these three things to calculate Q for the calorimeter. That's going to be typically the first step involved in any calorimetry problem. Then from there, what you do with that value of Q depends on the type of reaction that we're dealing with. All right, so the first type of calorimeter we're going to talk about is called a constant pressure calorimeter. And so this is one that can be designed fairly simply. The one you do in a lab is probably going to be like a thermos or a coffee cup calorimeter, as they call them, where it's just, again, the water inside the calorimeter is what absorbs the heat, some sort of insulated surroundings, which can be as simple as a coffee cup, and then a thermometer to measure a temperature change. And so in a constant pressure calorimeter, they're typically going to be vented. So you do lose a little bit of heat to the surroundings as a result. So they're not the most accurate type of calorimeter because they are vented, so some of the heat can leave. But because they're vented, that means the pressure is going to be constant during this process. All right, so they're vented and they're useful for processes occurring in the liquid or solid phase. You can't use them for gases very well because they're vented, so the gases will just all escape into the surroundings and not react like they're supposed to. But if you have a solution reaction or something that's happening in the solid phase or some combination of those two, then these are pretty simple and pretty useful for that. So one of the major applications of calorimetry, and especially this kind that's shown here, the more simple kind, would be to determine an unknown specific heat for a substance. So we have those specific heat capacities for every substance in the world. They can be measured. For water, it's 4.18. For every other substance is different. And how do you measure that? So usually for a calorimeter, what you can do is you can measure specific heat for a solid using this type of device. So the way that you do it is you heat up the solid first to some known temperature. Often you'll just you'll do it for like a piece of metal, something that doesn't dissolve in the water. It has to be something that doesn't dissolve in the water, but like a piece of metal or something that'll just sit there in the water. And you heat it up to some known temperature, usually 100 degrees Celsius, by boiling it in water. And then you take that hot piece of metal or whatever solid it is, and you place it into the calorimeter, which is filled with room temperature, colder water. So cold is a relative term here, but it's colder than the temperature of the solid that you're putting in. And then what you do is the measurements that you make are going to be the final and initial temperatures of the calorimeter itself with the thermometer that's in the calorimeter. So when you do a process like this, whenever you do heat transfer in a calorimeter, the heat that is absorbed or released by the substance that's in the calorimeter is going to be equal and opposite in sign to the heat that's released or absorbed by the calorimeter itself. So written mathematically, what this means is that the negative Q for the solid, the heat for the solid, is equal to the heat for the calorimeter. And so for the solid that you're putting in the calorimeter that you want to measure the heat capacity for, that can be written as MC delta T for the solid, with a minus sign in front. You need the minus sign on one side of the equation because the heat terms are going to be equal and opposite in sign. The solid is at a higher temperature, so it's going to give off heat to the calorimeter, and the calorimeter is at lower temperature, so it's going to absorb that heat. So the signs of the heat will be opposite, but they'll be the same in magnitude. So this term for the solid with a minus sign in front is equal to MC delta T for the water in the calorimeter. All right, so you basically do MC delta T, mass times heat capacity times delta T, for both the solid that you're putting into the calorimeter, which starts out at a higher temperature, and for the calorimeter, which starts out at a lower temperature and will increase. And the heat transfer will stop once the temperatures of the two are equal to each other. Yeah, question? Yeah, it's negative Q solid. Let me change these to bullet points. That doesn't confuse anybody. Yeah, so the negative heat of the solid is equal to the heat for the calorimeter. They're the same in magnitude, but they have to be opposite in sign because one of them is releasing heat, one of them is absorbing heat. So the signs will be inherently different. So you need the minus sign to make them equal to each other. But then what you can do, there's different ways of solving this, but we can then calculate the unknown heat capacity of the solid. So in this type of experiment, usually you're trying to find out what the heat capacity is for the solid. That's going to be your unknown. You measure how much solid you put into the calorimeter, you measure the change in temperature for both, you know the heat capacity for water, and so then you can just solve for this. So MC delta T for the calorimeter with a minus sign out in front, divided by the mass of the solid and its delta T. And again, you don't have to memorize these equations. They're all sort of built off of the key concepts of calorimetry, but that's how you would calculate the heat capacity of the solid. Okay, so let's see how that works in practice. So we have a 10-gram sample of a solid, and we heat it to 75 degrees Celsius, and then place it into a calorimeter that contains 50 grams of water initially at 25 degrees Celsius. So again, when we take a hot object, a hot piece of metal or whatever solid it is, and place it into the colder calorimeter, heat transfer is going to occur until the two temperatures are the same, until the temperature of the solid has decreased to the same temperature that the water has increased to. Once they're at the same temperature, heat transfer stops. So that final temperature is, we're told here, is 26.64 degrees Celsius. So the temperature of the water increases from that amount, and that would also be the final temperature of the solid after the heat transfer takes place. So with that information, what is the specific heat capacity of the solid? All right, so again, the concept is that the mass of the solid times the heat capacity of the solid times its delta T is equal in magnitude but opposite in sign to the mass of the water times its heat capacity times its delta T. In reality, we can put the minus sign on either side of the equation. I think mathematically it's slightly better to put it, well, I'll just do it this way so I don't screw up the math, because that's how I did it before. So as I said, one side of this equation needs a minus sign because the heat transfer is equal in magnitude between the two but opposite in sign. So you need a minus sign somewhere, but that's just what we're going to use. So then if we want to just solve for this algebraically before putting numbers in, or we can put numbers in first, however you prefer to do it, the heat capacity for the solid is equal to MC delta T for water with a minus sign in front of it to change the sign, divided by the mass of the solid times its delta T. All right, so everything else in this is going to be known. We just have our one unknown, which is the heat capacity of the solid that we're trying to find. So some of these are going to be given to us directly. So the mass of water in the calorimeter is 50 grams. That's stated directly in the problem, and you'll need to know that. Or sometimes it'll be in milliliters, but those numbers are the same. Heat capacity for water is given here, and just one you should know, 4.184. Then we need the two delta T terms as well. And then we have the mass of the solid in the bottom is 10 grams. So you need to know how much of that you're putting in there, which is 10.0 grams. So all we need are the two delta T terms for the water and the solid to be able to finish calculating this out. Okay? So delta T is always going to be final minus initial. So for the water, that's not delta H, it's delta T, sorry. Delta T for water is going to be the final temperature for the water. So the water is initially at 25 and it changes to 26.64. So that's the final temperature for the water is 26.64. The initial temperature is 25. So it's plus 1.64 degrees Celsius. And then for the solid, the object that we placed in the calorimeter, it's initially at 75 degrees Celsius. Now we don't specifically state the final temperature for the solid, but remember that the heat transfer stops when the temperature of the solid is equal to the temperature of the water that it's in. Because heat transfer is always when you have a difference between the two temperatures. So once the water temperature, if that's the final temperature for the water, that's also the final temperature for the solid after the heat transfer is stopped. So long story short, the final temperature for both substances is going to be the same, 26.64. But then the initial temperature for the solid was 75 degrees Celsius, so it's going to have a negative delta T because it's cooling down during this process. That's going to be minus 48.36 degrees Celsius. So we put those two in, we put 1.64 degrees Celsius for the delta T for the water, minus 48.36 delta T for the metal. Heat capacity should always be a solid number, or sorry, a positive number, so we have a negative over a negative, so that comes out to positive. And the value is going to be 0.709 joules per gram degree Celsius or gram Kelvin. And either unit is equivalent. So that's how we would calculate an unknown heat capacity. We measure the heat that's absorbed by the calorimeter, which is this top term here. Then we set that equal and opposite to the heat that's released by the object we put into the calorimeter. So that's one application of calorimetry. So any questions on that? All right, the next major application of calorimetry is going to be determining delta H. All right, so again, we just learned this today, but let's think about the definition of delta H. Where is that? All right, so for delta H, remember as we just said earlier today, it's delta E plus P delta V, which is equal to heat measured at constant pressure. So if you're doing a constant pressure calorimetry experiment where the calorimeter is at constant pressure, if you measure the heat, that directly measures delta H. So delta H is directly measured by constant pressure calorimetry. So if you do a chemical reaction inside of a calorimeter, and you do it at constant pressure and you measure the heat, then you're going to have a direct measure of delta H. All right, and so again, the steps are going to be pretty similar here. You measure the heat for the calorimeter, which is either just given as Q or QCal to designate it as heat for calorimeter. So that's the same as we just talked about. It's going to be the mass of the water in the calorimeter, heat capacity of the water, times delta T. So again, this whole term here is for the water that's in the calorimeter, plus whatever heat capacity you have for the calorimeter itself times delta T. So that's the heat that's going to be absorbed by the calorimeter. And again, depending on how the problem is set up, it's going to be some combination of these two terms. In some cases, we assume that all the heat is absorbed by water. If that's all you know, you just use that term. In some cases, we just group everything together into one big heat capacity, and we just do this second term here. Or in other cases, it's the sum of the two. So again, you have to use the information that's given to you in the problem to figure out how we calculate the heat for the calorimeter. But that's what's going to be the first step. Now then, the other thing to keep in mind is just like we saw for the last problem, the calorimeter is sort of like our surroundings. It's either absorbing heat from the reaction or giving heat to the reaction, and the reaction is our system. So those two heat terms are going to be equal in magnitude but opposite in sign. So the heat for the reaction is going to be equal to the negative of the heat for the calorimeter. But of course, how much heat the reaction either releases or absorbs depends on the scale that the reaction is done on. So if you react a tiny amount of substance, it's going to produce just a little bit of heat. If you react a large amount of substance, it's going to produce a lot of heat or absorb a lot of heat depending on the sign of Q. So this value that we measure depends on the scale of the reaction we're doing. So that's not very useful because if we want to compare enthalpy changes or heats for two different reactions that are occurring on 2 different days, but they're, the scales are different, everything is, it's not an apples to apples comparison. So the way that we calculate delta H,
What's that say before, like the negative Q with Cal, like
Q reaction. So Q RXN is an abbreviation for heat of reaction. So the heat of the reaction is equal to the negative of the heat for the calorimeter. So again, we calculate the heat for the calorimeter first using the data that we collect for that experiment. And then what the significance of that is that it's equal in magnitude but opposite in sign to the heat for the chemical reaction that we're studying. But then delta H is not just going to be this heat of reaction, because that depends on scale. It's going to be the heat of reaction divided by the moles of the product that's formed. So you can normalize it in different ways, but usually it's pretty obvious how to do this, but we have to divide by moles of product. So delta H is going to be typically reported as a heat term in joules or kilojoules per mole of substance that's involved in that reaction. And I guess more generally, I'll just say moles of substance here. It's not always a product, but it'll be obvious from the problem how you should normalize this. So it's always going to be divided by moles of substance at the end to get delta H in terms of an amount per mole of substance. All All right, so here's an example of a calorimetry problem and how we use that then. So a lot of the steps are the same as the first one we did, but now we have to set it in equal to a delta H. So we take 1 gram of ammonium chloride and we add it to a calorimeter containing 50 milliliters of water. And then the final temperature is, so it starts at 22.3 Celsius, and then the final temperature is 20.98. So the temperature is decreasing during this process. So we want to know what is the enthalpy of dissolution for NH4Cl. So this time we're not actually doing a real chemical reaction, we're just dissolving something in water. And sometimes when you dissolve things in water, there is going to be heat absorbed or released during that process. So here we're trying to calculate that for NH4Cl per mole of substance. How much heat is absorbed or released per mole of substance, enthalpy more specifically. So again, all we're doing here is we're taking solid ammonium chloride, dissolving it in water to make aqueous ammonium chloride, and during the process of dissolving this, it's going to have some enthalpy change, delta H, that we're trying to calculate here. So again, there's going to be heat either absorbed or released. Because the temperature of the surroundings is decreasing, that means the sign of delta H should be positive. We'll make sure that's true at the end, but we'll get to that actual value here in a minute. So again, the first thing that we're going to do is calculate the heat for the calorimeter. In any calorimetry problem, we want to calculate heat for calorimeter. That's typically the first step. So we take the mass of the water in the calorimeter, heat capacity of the water, and delta T for that. And then the heat capacity of the calorimeter itself times delta T. Now again, which of these two terms you use, one or both, depends on the information that you're given in the problem. In this problem, we're telling you that there's 50 milliliters of water in the calorimeter, so we know how much water is present. But did we tell you anything in this problem about the heat capacity of the calorimeter itself? Does anybody see that anywhere? All right, so I see some head shaking, and you're correct that there is no information provided about the heat capacity of the calorimeter. We just know how much water is in there, and that's it. So this is going to be a problem where we don't have to account for that second term there. Again, depending on how the problem is set up, you may use one or both of those. So we're just going to account for the water in the calorimeter. So when we're calculating the heat for the calorimeter, we just take the mass of the water, which is 50 grams. 50 milliliters is equal to 50 grams of water because the density is 1. The heat capacity of water is 4.184. That was given here, and it's one you should know. And then delta T. So delta T is going to be the final minus initial. So the final temperature is 20.98 degrees Celsius, directly stated as final temperature in the problem, and initial temperature is 22.3. So temperature is decreasing, so we have a negative delta T, which is minus 1.32 degrees Celsius. So in this case, the heat for the calorimeter is negative, and it comes out to minus 276 joules. Okay, so that's Q for the calorimeter. It's a negative number this time. And then as we said, the heat for whatever reaction we're studying, technically not a reaction here, but we're just dissolving a substance, but remember it's equal to the negative of the heat for the calorimeter. So if the heat for the calorimeter is negative 276, the heat for the reaction is positive 276. But again, that's the amount of heat that's absorbed when 1 gram of ammonium chloride dissolves in water. What we're looking for here is the delta H in kilojoules per mole of ammonium chloride. So we need to convert this grams into moles and divide the two. So the delta H for this is going to be the heat for the reaction divided by the moles of the substance we're dissolving, which is ammonium chloride. We want it per mole of ammonium chloride. And so we're going to take that number here, plus 276 joules, and divide it by the moles of substance. So we have grams of ammonium chloride. I'm running out of room here, but the moles of ammonium chloride are, we have 1 gram of that substance in this experiment. And then the molar mass is given as 53.94. So 1 mole has a mass of 53.94 grams. And so the moles is going to be 0.0187. All right, so that's how many moles of substance we use. So if we divide the heat for the reaction by the moles of substance, that will give us delta H in joules per mole. And then we just have to multiply or divide by 1,000 to get it into kilojoules. So if I did the math right, what I got was positive 14.8 kilojoules per mole. All right, so there are a decent number of steps in these problems that we have to keep straight, but it is, again, helpful to make sure that the sign is at least correct. So in this problem, we said the temperature of the water decreased. Whenever the temperature of the surroundings decreases, that means it's an endothermic reaction. Heat is going into the reaction from the surroundings, and that means it should be a positive delta H, which is what we got here. So at the very least, you can make sure your sign is correctly just by looking at conceptually the information, but the steps to get this, again, 2 major steps: heat for the calorimeter, and then dividing that by the moles of substance and changing the sign to get it to the correct sign. All right, so any questions on that? Yeah.
Wait, plus stuff for the calorimeter at the top, it's like, is that always going to happen whenever we are not given that?
Yeah, so if we don't tell you the heat capacity of the calorimeter, so you always have the heat capacity for water. So if you know how much water is in there, you always have to account for that using this first term here. But if we don't tell you the heat capacity of the calorimeter, then of course you can't account for it, and you're basically making the approximation that all the heat is absorbed by the water, which is going to lead to some inaccuracy if you're doing this experimentally, but in this problem that's the best we can do because we don't have the heat capacity of the calorimeter. All right, so that's an example like that. How much time do I have? We're running low on time, so I'll have to push off some of this. All right, let's do this last problem here and wrap it up. So this is another one here, which is simple. So we take 50 milliliters of HCl, and then we add solid NaOH, so we're going to do an acid-base reaction here. And then we want to know that, and the temperature increases by 7.27 degrees Celsius. What is the heat of reaction in kilojoules per mole of water formed? All right, so in this case, we are actually doing a reaction, and it's one that we should recognize from chapter 6. Aqueous hydrogen chloride plus HCl, hydrochloric acid, plus sodium hydroxide, making water and NaCl. So this one is balanced with coefficients of 1, so we don't need coefficients here. And again, we're looking for kilojoules per mole of water that are formed. So we can always calculate the heat for the calorimeter first if we want to. We should always have the information we need to do that. So in this case, it's going to be, again, the same story as last time. We need to account for 2 possible terms here. But just like the last one, we're not telling you what the heat capacity of the calorimeter is. We're telling you how much water we're using. It's an aqueous solution with 50 milliliters. That's going to be mostly water, so we'll assume that we have 50 milliliters of water again, even though there's some HCl dissolved in there. But we don't see anything about the heat capacity of the calorimeter. So again, we can leave this term out. So just like last one, we have 50 grams of water or 50 milliliters. Heat capacity, again, we're not told anything differently, so we'll just assume that we have the same heat capacity as water. We're telling you to assume that the solution has the same heat capacity of water, which again is not exactly correct, but will be close to correct. And then the temperature change we're giving here directly is 7.27 Celsius. So we got a heat for the calorimeter of 1521 joules. And that means that the heat for the reaction then is the negative of that, which is minus 1521 joules. But again, what we want to find out in this problem is delta H per mole of water formed. So now we have to do a little bit of stoichiometry to figure out how much water is formed in this reaction. So we have amounts for both substances, so we have to calculate moles of each. So for the HCl, we have 50 milliliters. And the molarity is 1. So we have 1 mole of HCl per 1,000 milliliters. So this is a review of chapter 6 stuff now that we just covered. So moles of HCl is going to be 0.05. And then for the moles of sodium hydroxide that we add, we have 1.60 grams, or sorry, yeah, sodium hydroxide. We add that as a solid. And the molar mass of that is 40. So we're going to use the molar mass to convert grams to moles for sodium hydroxide. So we get 0.0400 moles of NaOH. So this is a one-to-one reaction. So without having to do too much detailed stoichiometry, we have fewer moles of sodium hydroxide, so that has to be our limiting reactant. And if we're reacting 0.04 moles of sodium hydroxide, how many moles of water do we form? Same amount, 0.04, it's a one-to-one reaction. So because it's one-to-one reaction, this is our limiting reactant, because there's fewer number of moles, and because it's one-to-one reaction, that's how many moles of product we form. So finally then we can calculate delta H as the heat of the reaction divided by the moles of the water we form. So our heat of reaction we determined up here was minus 1521 joules. The moles of product that we're forming, moles of water in this case, is 0.04. That'll be true for either product. And then if we want it in kilojoules per mole, we have to, again, divide by 1,000. So it's going to be minus 38.0 kilojoules per mole. All right, so the series of steps were similar in that one. We just had to account for, in this case, the limiting reagent being sodium hydroxide to figure out how much moles a product actually forms to be able to then get the delta H correctly normalized to that amount. All right, so that takes us to the end of that. So I will do a couple more examples next time to sort of drive home some of these points, and we'll move on to the next topics in this chapter. Later.